Why are certain foods, like chocolate, always wrapped in a layer of shiny silver foil? Wait a minute, isn't metal one of the best conductors of heat? So how can something that transmits heat so well actually protect the chocolate from heat? Or consider this familiar sight, that warm, delicious takeout meal delivered in a container made of a thin sheet of aluminum. Have you ever stopped to wonder what that foil is actually doing? How can it block heat when it's made of metal, and metals are supposed to be top-notch heat transmitters? This is a fascinating scientific contradiction, and today we're going to pull back the curtain on its secret. Here's a taste of the interesting topics we'll cover in this video. Cold and heat are just feelings. The methods of heat transfer. Infrared radiation, the invisible heat. When did aluminum foil first enter our lives? To truly understand how aluminum foil works, let's first ask, what exactly is heat? Heat is caused by the vibration of molecules, and because the molecules in all objects vibrate, all objects produce some amount of heat. Every object in the universe, from your skin to the wall of your house, is constantly emitting heat, even when you perceive it as cold. Even snow or ice still have a tiny bit of heat energy. As a result, there is technically no such thing as cold in the universe. Cold is born from your perception. Surprised? Let me explain more, but first, let's cover the three main ways heat is transferred. One of these methods is conduction. This happens when two objects are in direct contact. You know this one very well. When you touch a hot mug and burn your hand, conduction is the direct culprit. The faster vibration of the hot water molecules caused the molecules of the mug to vibrate quickly. And when you touched it, this violent vibration was transferred to the molecules of your fingers. Now, you must be asking, if ice also has heat, why don't our hands feel warm when we touch it? Because heat is a sensation. The intensity of the ice molecule's vibration is less than that of your hand's molecule's vibration. When you touch the ice's molecular vibration intensifies, its temperature increases, and it starts to melt. In contrast, the vibration intensity of your finger molecules decreases, and that is what you perceive as the feeling of cold. So the feeling of cold is just your brain comparing the amount of heat in your fingers to the amount of heat in the object you're touching. Now that we understand heat is just a feeling, let's phrase the sentence I said at the start of the video more scientifically. Any object whose molecules vibrate has a temperature, not just heat. Now we get to another, much more interesting method of heat transfer that requires no physical matter: radiation. This is the transfer of heat through a type of light that is invisible to our eyes. Every object that has a temperature and whose temperature is above absolute zero, or minus 273.15 degrees Celsius, emits infrared waves. The hotter the object, the more infrared radiation it emits. Absolute zero, or 0 Kelvin, is the coldest possible temperature, and there is no colder point in the world. This is the state where molecules have no vibration and molecular motion drops to zero. That is why it is called absolute zero, and in honor of the scientist who discovered this phenomenon, William Thomson Kelvin, known as Lord Kelvin, it is named 0 Kelvin. Now that we know infrared is a form of heat, let's refine that first scientific statement even further. Any object whose molecules vibrate has a temperature, and therefore also has infrared radiation. Infrared radiation is part of the electromagnetic spectrum, just like the colors we see, but its wavelength is a little longer than red light, which is why, as we said, it's invisible to us. When you stand in the sun and feel warm, you are actually receiving the sun's heat in the form of infrared radiation. Your hot takeout food does the same thing. It sends heat out to its surroundings as infrared radiation. Speaking of seeing colors, we've also made a video about color perception. Do we all see colors the same way? Is the color blue that I see the same as the blue you see? If you want the answers, check out that video. We've put the link in the description section. Let's get back to our favorite treat, chocolate. To answer the question of what the foil's role is, we must first know chocolate's archenemy, infrared radiation. When a chocolate bar is placed in a warm environment, infrared radiation from the surroundings reaches it. This radiation causes the chocolate molecules to vibrate, and this vibration is what raises its temperature and causes it to melt. So, what does aluminum foil do? Aluminum is a metal with a very smooth and shiny surface. Aluminum foil practically rejects infrared radiation entirely. The foil's bright surface can reflect 90 to 95% of the ambient infrared radiation. This means if sunlight or ambient heat reaches the chocolate, most of it bounces right back into the environment without being absorbed by the chocolate and causing it to heat up. And aluminum foil does the exact opposite for containers of hot food. It acts like a mirror. Any infrared radiation leaving the hot food and hitting the foil's inner surface is reflected right back toward the food itself. This way, instead of the heat escaping into the environment, it gets trapped, keeping your food warm for a much longer time. Now, for an interesting point. Based on everything we've said so far, you might conclude that if you hold the chocolate wrapper in your hand or place it on a warm surface or even in hot air, there's no infrared radiation coming from the contact. So the foil shouldn't do much, and heat transfer should happen through conduction, direct contact with the warm object, heating up the chocolate, right? Wrong. Contrary to your expectation, the aluminum foil works here too and prevents the chocolate from heating up. Before I tell you how, let me introduce you to the third method of heat transfer, convection. Convection is a form of heat transfer that occurs through the movement of fluids, meaning liquids or gases. This is how it works. When a gas or liquid near a heat source heats up, its density decreases, causing it to rise, and colder fluid takes its place. This continuous cycle transfers heat. You've definitely felt the hot air rising when you sit next to a fireplace or a space heater. This is also how water in a pot on the stove heats up uniformly. In food containers, the aluminum foil, by completely covering the meal, creates a physical barrier. The foil traps the air near the surface of the food and prevents the free circulation of air and the escape of heat through convection. By doing this, the foil effectively blocks the main escape route for heat, the warm air currents, and keeps your food warm, just like a blanket prevents you from feeling cold. In the case of chocolate, aluminum foil does the exact opposite. By trapping a thin layer of air, it prevents heat from reaching the chocolate. It acts like a double-paned window that slows down heat transfer. To put it simply, the foil does two jobs: reflecting infrared radiation and restricting air movement to prevent convection. The combination of these two actions ensures less heat reaches the chocolate and food in a container stays warm. Here's a practical warning. Conduction is the foil's Achilles heel. For effective insulation, there must be a thin layer of air between the foil and your food. If the foil is pressed directly and firmly against the food, heat can quickly escape through conduction. That's why liquid foods shouldn't be kept in a foil container. They will cool down very quickly. Now that we understand aluminum foil was a brilliant invention, whose genius idea was it? Which company first thought of using this creative method to keep food fresh? It's interesting to note that this simple idea has a rather fascinating history. In the early 20th century, Swiss chocolate manufacturers faced a big problem. The chocolate bars were melting during transport. At the time, most packaging was made of tin, but its production was expensive and the material was scarce. In 1910, the Swiss company Dr. Lauber, Neher, and CA introduced an industrial method for producing very thin aluminum foil. Shortly after, the Tobler company, which makes the famous Toblerone chocolates, was the first factory to adopt this foil for chocolate packaging. A few years later, Nestlé also used the method, and aluminum foil quickly replaced tin across Europe. In addition to being cheaper, aluminum was lighter and surprisingly hygienic. This material protected food not only from heat, but also from light, moisture, and oxygen. This meant that the chocolates retained their flavor, color, and aroma for much longer. From then until today, this simple technology has been repeated billions of times and remains one of the most effective ways to protect food. So every time you unwrap a foil-covered chocolate, you are peeling back one of the most ingenious physical shields ever made by humans, one that even has many uses in space. Speaking of space, we have a very interesting video about spacesuits. We've put the link in the description. We would be honored if you watched that one too. This simple aluminum foil, designed based on the laws of physics and a deep understanding of heat transfer, is engineered to defeat heat, light, and air, and deliver the sweet flavor of chocolate safely to you. Sometimes the shine of these thin foils is a sign of the elegance of science serving the small, enjoyable things in life. Our world is full of amazing and sometimes incredible stories. If you found this video interesting, please like it and share it with your friends. Be sure to write your comments and questions in the comment section. We'd love to know which part of this story was most interesting or surprising to you. Stay curious until the next video.